Hi, everyone. I'm Melissa Callis of the Advanced Photonics Coalition. Welcome to our webcast, an ecosystem perspective of integrated photonics for the AI revolution. This webcast is an outreach to everyone watching this video. We must collaborate and create standards in order to move our industry forward and to scale PIC technology to volumes. The only way this is going to happen is if all of us work together, and the Advanced Photonics Coalition provides the neutral ground to work with. This webcast will also be a live panel at OFC in San Diego, so we encourage you to come out and see us live in person in March. I'd like to thank all the participants of this video, including Jose Pozo of Optica for hosting it, and Nancy Lima of the DuPont Silicon Valley Technical Center for producing it. The slides are available now at advanced-photonics.org if you'd like to take a closer look at those. And we thank you so much for joining us.
My name is Jose Pozo. I'm the Chief Technology Officer of Optica, the Global Photonic and Optics Industry and Academic Organization, and I had the honor and pleasure to be here today with you for a very important meeting. Over the next 2 hours, we are going to have a witnessing of how the photonic industry is addressing the AI revolution. This meeting is organized by the Advanced Photonics Coalition. And in a couple of minutes, you're going to hear about what this is and how it can benefit your business. Being part of the Advanced Photonics Coalition is something that Optica endorses for developing your business in the field of optics and photonics for datacom. But on the next 2 hours, listen to this. We wanted to have the entire value chain represented for the AI revolution. For example, for the Foundry, we're going to have GlobalFoundries represented by Vikas Gupta. For the OSAT, we're going to have Silitronics with Dhiraj. As a contract manufacturer, the company that everyone is talking about, we are going to have Jabil represented by Noam Ophir. And also we wanted to understand the views from the equipment manufacturer perspective. And for that, we have none other than the CEO of Ficontec, Torsten Varenkamp. And since one of the challenges, perhaps the main challenge, is testing, Quantifi Photonics will be there represented by my very good friend, Kees Propstra. And in every value chain, you need to have the customer. And for that, we are honored with the pressure of Manish Mehta from Broadcom. This event is going to take exactly 2 hours of your time, and every minute will count. I would like to remind you that if you have any questions, and you should have questions, please use the Q&A button, and always in your question, answer the person that you want the question to be addressed to. Very important. Please tell us who in the room should answer such question. Or we're going to have plenty of questions. And after this event, we're going to have a panel at OFC, and you're going to hear more about that later on. But now, I would like to give the floor to the chairman of the Advanced Photonic Coalition, my personal friend, and a person who has meant the world to first the Cobo Alliance, now APC, and who has a passion to bring companies together. Jeff, the floor and the attention of everyone is yours. Tell us what is APC.
Hello. Yes, let me share my presentation.
We can see it. Just go presentation mode.
Yeah, it takes time. All right. So I'm Jeffrey Maki, Vice President and Treasurer of Advanced Photonics Coalition. We are previously known as COBO, but today we are APC. The purpose of the corporation is to improve business conditions for and sorry, my screen is not behaving properly. Yeah, so business conditions for and promote the common business interests of persons developing, manufacturing, integrating, and using optical interconnects and optical subassemblies in network equipment for data center, high performance computing, quantum computing, artificial intelligence, and machine learning applications. So that's our purpose. You can find that in our corporate documents. But really our mission then is for working with optical fabs so they can be leading and creating the world's best technology in terms of reliability, validation, and trust, trust being the collaboration to achieve those objectives. So this allows for the creation of building blocks for silicon photonics ICs that are put together in an assured way using Foundry process development kit to accelerate production. Okay, that all sounds good, but we need more than that. What we see in the industry is an ecosystem that achieves that. And we have different levels in the ecosystem. We have the hyperscalers and service providers that are the end customers. And some of these are also functioning themselves as system companies, putting out requirements for technology. And then we have the traditional system companies. And as we drop down through this ecosystem, we now have the photonic foundries playing a very important role for our silicon photonics components and module builds and so on. And so in this ecosystem, we have modules, the OSAT, and active and passive components. So this entire ecosystem, at every level of it, can benefit from standards. Standards help to drive access to technology and also multi-sourcing capability so that we can, as an industry, drive volume. The whole idea here is to break away from silos. We'd say silicon photonics, then it'd be like, well, which one? And that means then the access to silicon photonics was limited in volume because we only have the access of that one particular silo. So now if we can work at each level of this ecosystem to use standards to break out of these silos, we can now drive larger volume and cost reduction for the industry. And the commonality then hopefully will bring us to a very vibrant industry different than we've been seeing. So our whole premise now at APC is to be helping every level of the ecosystem to recognize where the opportunity of standards has been, but not yet exercised, and indeed exercise that opportunity. So we have a number of companies that are a member of APC, and we're growing in the number of members. And so looking forward then to hearing from more companies that wish to join. And today, many of our presenters are already members of APC. So thank you for your attention. I hope I have made it clear we're here to help. Thank you.
Thank you very much, Jeff. As I said before, for me, it is very important that you understand the value of APC. Many of you are corporate members of Optica. APC is here to make an iteration on connecting the supply chain and address challenges go from the de facto standards all the way to understand the challenges of one part of the supply chain to the needs of the next one. And that is why we are meeting together, to have an example of a supply chain and understand how a company will have potential suppliers and customers and how they can work together to solve the overall AI challenge. And to start with, let's start with a company that really has meant the success of silicon photonics. When GlobalFoundries said to everyone, we offer silicon photonic production, was when companies realized that the volume production demanded by the applications was there. When they decided to go into quantum technologies, that's when companies realized that quantum technology was something serious. Today, they are here to understand how silicon photonics can address the AI challenge. None other than GlobalFoundries will be represented by Vikas Gupta. Vikas, thank you very much for being with us today. The floor and the attention of everyone goes to GlobalFoundries. The floor is yours.
Thank you very much, Jeff. Let me share my presentation. Hopefully, everybody can see it. I'm going to put it in. Okay. So hi, my name is Vikas Gupta. I'm the Senior Director of Product Management focused on silicon photonics at GlobalFoundries. And today I'm going to use my 10 minutes to give a perspective on the foundry and an ecosystem view of silicon photonics. So let me just start by making a statement that AI model size, the compute systems that are required to actually run these models are also becoming very complex. And one of the key sort of items that is holding some of these systems back is the interconnect. And the interconnect, basically, the requirements are, high energy efficiency, low loss, and high speed. And silicon photonics as a technology can meet these requirements. So what I'm going to do is cover two topics. Just give you all a brief overview of GF Photonics. That is the brand name of the photonics technology, silicon photonics technology that GlobalFoundries offers. And then I'll put it in perspective. And what GF is doing as a company, but then also what the industry needs to step up with respect to the ecosystem. So let me just start off by overview of the photonics technology that GlobalFoundries offers. So you can think about GF Photonics as a bit of a systems on a chip. And what we've done is we've integrated electronics and photonics on a 300 millimeter wafer, SOI wafer. And so you can see in this diagram on the left, the electronic components represented by the NFET and the PFET. But then we also have pre-characterized devices, such as active devices, such as modulators and detectors. On the right, there is a fairly large suite of silicon waveguides and silicon nitride waveguides. We've also introduced the whole concept of undercut for our heaters to make the heaters more efficient. And in addition to that, we have technologies for light in, light out. Our plan of record technology is a V-groove based passive fiber attach. We're going to upgrade this V-groove based fiber attach to include a silicon nitride spot size converter for high power requirements. And there is work in terms of R&D in terms of attaching an on-die laser. So all of this provides sort of all of the building blocks that a company would need to be able to produce high-speed optical links. Now, in addition to these components, device components, we've also paid attention to packaging. And so towards that, we have included things like copper pillar, we're working on TSVs, and the ability to do on-wafer testing. And I will go into some of those details a little more into the presentation. Now, one of the things that I wanted to point out is that we have taken a platform approach to silicon photonics. And what that means is that we have these pre-characterized devices as part of our PDK with the intention of doing two things. One is, getting things first time right. And the second thing is ease and speed up the introduction of products that our customers may be designing to. Now, the flexibility of this technology comes to the forefront when we start talking about different architectures that can be implemented on this technology with almost no modification. So typically, high-speed interconnects can be divided into sort of two categories: the fast and narrow, which requires electrical scaling, and the slow and wide, which is sort of optical scaling. The electrical scaling basically requires you to have a high-speed electrical signal. That electrical signal is imprinted on a laser output, and you're transmitting the same speed of that electrical signal onto the fiber. In terms of the slow and wide, you can think of that as DWDM, or dense wave division multiplexing. And you're basically taking a low speed electrical signal, sort of parallel electrical signal, muxing all of those signals onto a fiber using different wavelengths of the laser. So the beauty of this platform approach is the fact that you can sort of meld these two architectures and produce these two architectures with very little in terms of customization of the technology. And all of these components, like the V-groove, the ability of whether you want a modulator, which is a ring modulator, or a Mach-Zehnder modulator, and all of the components that you would be required to put together these sort of circuits are part of the PDK and part of the offering that GF offers. So with that, I'm going to go I just wanted to give you all a flavor of the technology that GF offers, but I want to focus most of my presentation about the ecosystem that GF is working towards, but then also demands that we may have from the industry. So towards that, let me just start off with a definition of ecosystem. It is a complicated system. It requires, different companies to work together. Each company may be specialized in their own sort of field of view, but then it also there's a high level of interdependency between these companies. And so what I've tried to do in this chart is just show you sort of the larger context of all of the players that potentially may be involved. Some of them will be talking today.
I think we have lost connection with GlobalFoundries or leading foundry facility. Let's wait a couple of minutes, but in the meantime, let me remind all our audience, for any questions that you have, please use the Q&A button and there write the person you want to direct the question to. At the end of the meeting, exactly at 11:22 Eastern, we'll have a Q&A session in which we'll address every single question that you ask. And that's always the most exciting part of the event. Vikas, are you with us? I think we are in this moment, which this is the moment in which we excel on making sure that people understand this is a live event. And in live event, things happen. And this is why we need a more reliable internet connection for the world. And so we're trying to solve here. In the meantime, let me continue with the program and we'll come back to Vikas in a second from GlobalFoundries. But now we started with the Foundry and we are going to continue with the OSAT. Why? Because the OSAT is the one that gets the chips from the foundry, will get the equipment from Ficontec and other equipment suppliers, and will provide packaged devices. This is the next step in the supply chain. For the OSAT, we went to a company that is interacting in many different markets, Datacom, LiDAR. We go to Silitronics. Thank you very much, Dhiraj Vora and Cassandra, for being with us today. Tell us how you take over from GlobalFoundries and you are the next step in the supply chain. The floor and the attention of everyone is yours.
Perfect. Thank you, Jose and Optica team for putting together such a great webinar.
And the Advanced Photonics Coalition, the one organizing the event today.
Advanced Photonics Coalition. Thank you for inviting Silitronics. We are proud of being a part of the great presenters here. GlobalFoundries already talked about the PIC. We are talking about OSATs and what is needed from OSAT point of view. So we are going to talk about the challenges in integrated photonic assembly. I'm going to give that initial introduction, and then Cassandra is going to talk about the engineering. The outline of our project is that we are going to talk about quickly what is the OSAT model, and then what Silitronics has done so far in terms of the market. We'll quickly touch on the outlook. What are the challenges when we are talking about the photonics assembly, and how Silitronics engineering team has come up with a couple of solutions which will enable photonic PIC assembly faster, which are much higher yield. And then we'll talk about the summary. Quickly, normally outsourcing means, OSAT means outsourcing with a third party, and normally these are up in Far East. The role of OSAT is, optimize the process in terms of yield, cycle time, and they take advantage of economy of scale to bring down the cost. With the normal OSAT, in IC, they do the IC packaging, whether it's flip chip, wire bonding, then the test, and then obviously inspection during the assembly and before the final shipment. On the optical, it's still a growing market. So we have PIC, we got laser, we got waveguides. So all these need to be integrated together in terms of the package. And then we need to do pre and post testing while you're doing the active alignment. And the inspection is very, very key because you are talking about the lasers, you're talking about the waveguide, and then the fibers, where you have to do multiple inspection at incoming, during the process, and outgoing. Any little scratch in the optical path obviously will affect the power and the performance. So in a new OSAT, where you're talking about the optical IC and the photonics IC, that's where we are going to focus today in terms of what is the turnkey service. So turnkey means design, fabrication, assembly, and test, all being under one roof for OSAT. And normally OSAT will take over when the process is mature and is ready for high volume. For silicon photonics, as we all know, market is developing, is growing, but is nowhere close to the IC packaging. So today we are going to focus on silicon photonics. Offline we can talk about the design, assembly, and the test. But today we are going to talk about what are the challenges on silicon photonics. Before we talk about silicon photonics, there are multiple applications. Normally started with the telecom application, then cloud data transfer, lately AI ML. Meantime, we have customers in LiDAR as well as in industrial. So the application of silicon photonics is growing in multiple folds, and that obviously create a good opportunity for the OSATs. So as you can see, the market is growing and growing in multiple fold for next 10 years, and that is the time for large OSATs to bring in their know-how from the IC packaging, and then continue to understand and integrate optical assembly within the same facility. And as the OSATs are coming in, like Silitronics or AC of the world, and then comes Jabil, where they are doing the whole system level integration. So as the industry grows, obviously there are challenges. Without the, if you don't resolve the challenges up front, then scaling in high volume will be very difficult. So talking about the challenges, we have Cassandra, who is leading multiple process development across the board, whether those are cloud customers or silicon photonics or LiDAR. So she's going to talk about the challenges and how Silitronics engineering team has been helping customer to mitigate these challenges. So go ahead, Cassandra.
So when compared to standard OSAT processes, think IC wire bond and IC flip chip, the PIC photonics assembly and everything that comes in with it becomes substantially more difficult. So first of all, it's understanding that's a newer market. There's fewer standards. There's many more things to worry about. And this really affects your time and your timeline for doing everything from prototypes to MPI to DOEs. And these variables really do affect the entire process. So just from a very technical perspective, first, wire bond and flip chip generally can be considered to have three placement critical axes. Rotation also matters, but it matters much less than linear position. But adding these three more axes, sometimes with very tight tolerances, really increases exponentially the challenge assembly. Then there's also the issue that many of the current automated assembly machines are designed to be a custom solution that's designed for one product and is expected to continue along with that product. And then on the other hand, reconfigurable platforms tend to be more lab-grade solutions, which aren't really suitable for doing actual automated production with any sort of repeatability. This increases the time to do development DOEs to get to production. And optical packaging is also more highly disciplinary than the other sorts of packaging that OSATs traditionally do. There's more, obviously, optical engineering required, but there's also algorithmic engineering. A lot of these processes that used to be very vision alignment based, and you could kind of eat the tolerance losses, now require more algorithmic searches and very tuned in profiles. There's also the issue that the materials, there's just many, many more of them. It's partially, again, because it's an emerging industry, but it makes it much harder for an OSAT to stock a standard BOM. Right, so for wire bond, you essentially have two sliders. You have material and you have thickness. And then you have different machines that can make different types of bond heads. But for photonics, you have your wavelength, you have intensity, you have pitch, type, and you also have all of these different types of couplers, different foundries, different applications have different couplers. Couplers need different types of epoxies. Sometimes you need multiple epoxies per optical path. All of these mean that it's much harder for an OSAT to actually stock parts. We typically would get people to come in, and in any other type of assembly, they would assume that we have material, but in this one, it's much less likely than we actually do. Back to kind of the engineering challenges, there's just much more NRE that has to be done before photonic assembly. Everything more or less has to be custom, just given the tolerances required to be actually manipulating these things in 3 dimensions. And there's also just the reconfiguration of these machines. Most wire bond jobs or most flip chip jobs can be done with machine as is. Photonics jobs mostly can't. There's a lot of vision alignment. There's a lot of curing that has to be done in that. And there's obviously still the process and there's optimization within it. So we have a few solutions and mitigating factors. The biggest one is going to your OSAT before you actually tape out. And kind of doing DFM with them. And that way you can resolve a lot of issues before they actually come up. You can change designs or the OSAT can prepare in some sort of way. Silitronics is also partnering with Ficontec just to kind of unite our engineering abilities and more on an OSAT perspective. And the other thing is just that a lot of the times recently you see these teams still come to the OSAT for wire bond or flip chip, and they try to do optical assembly in-house using a lab-grade setup. But we're seeing that really reduces yield and it can increase handling damage and obviously increase cycle times. So the other thing is that there's a lot of different capabilities you need. I'll kind of burn through this because I already talked about it, but essentially there's a million different types of things that need to be assembled together in optics. And importantly, it needs to be an automatic and repeatable process. So you're actually hitting those yields and you're getting good loss characteristics. I'll hand it back to Dhiraj for more of the business angle after this.
Thank you, Cassandra, talking about the challenges and some of the must-have in order for OSAT to ramp up in high volume. I think the key message on this is that DFM is a must, especially before the tape out, so that Silitronics or OSAT can help the location of the fiducial, the thickness of the PIC, the location of the waveguides, the size of the fiber, the active alignment process, the tooling for grippers. So there are so many variables which need to be addressed upfront so that it's easy to ramp up down the road for high volume. Here is one of the case study we have done for one of our cloud customers, where you can see that the true mix of the Photonics IC and the regular IC along with the fiber array is happening, and the integration is happening more and more across the board. We have experience to help customers from designing the substrate, fabrication, PIC assembly, active alignment using Ficontec with multiple FAUs. We have done anywhere from 1/8 to almost 1/40 FAU for active alignment. At the same time, tooling is equally important. And in order to have all this process development, OSAT needs a facility where you have everything under a clean room. More importantly, having both the IC and the PIC assembly under one roof is also the IP protection and the collaboration between the customers and the OSAT. For us, because the applications is so much varies from silicon photonics to cloud, and customers also have a lot of hands-on experience while we're talking about the photonic assembly. So we allow customers, engineers to come to our facility and develop the process together side by side, as we have multiple Ficontec systems in-house. And one of the reason is the IP protection, so that each customers are having a dedicated machine. And once you have the full turnkey under one roof, then definitely that helps to reduce the cycle time, and that will help to ramp up for the OSAT. And my last slide for today is the market for silicon photonics is growing. And as the market grows, OSATs are definitely finding their niche and finding the role how to go with millions of units per month. Eventually, hopefully, it will go to billions unit per month. But before that, I think it's equally important to have the right OSAT partners where they have all the capabilities, and that will reduce the development time for the customer as well as ramp up for the OSAT models. And at the same time, the silicon photonics industry and applications are growing. Definitely, there need to be more active alignment system. There need to be more wafer level testing. There need to be more incoming, whether it's a 3D X-ray or doing the inspection 200x of the PIC on the sites. So a lot of opportunities for not only for the OSAT, but also the equipment suppliers. As the industry mature for photonics, the investment will be continued needed. From Silitronics point of view, we have made several investment, which helping us to establish OSAT in terms of USA. And these investment have definitely won the confidence from our customers. And as we are helping our customers, our learning curve is getting wider and obviously deeper. And as a result, we have been winning confidence from hyperscalers, tier 1, tier OEMs, as well as many leading startups. And with these startups to support, as I said, IP protection and co-development in Silitronics is equally important. So that's how we see the OSAT business model and ecosystem is developing for the next few years. And definitely, we are here to support and help our customers as much as we can. Obviously, for OSAT, having everything one roof or under one purchase order, as you say, is equally important. So thank you for the opportunity, and thank you, Jose.
Thank you very much, Dhiraj. Let me remind everyone, for all the questions you have for Dhiraj and Cassandra, please write them using the Q&A button exactly at 11:22 Pacific time. We are going to go through all the questions, make sure you get the answers that you need. But before that, Dhiraj, just one quick question for you. Many of your customers, all your customers, demand that all the chips, packaged chips that they get from you are properly tested. To what extent is testing still a challenge when it comes to the OSAT?
Yes, that's a very good question. When it comes to the IC packaging, the testing is very straightforward. You just do open short test. For optical testing, it's still a growing application. A lot of customers are doing testing in-house because there's a lot of IP involved. Recently, we start working and bringing in more testing equipments by working with the Quantifi so that we can start supporting customers in-house to shorten the true, the process development time. So yeah, we customers are asking us more and more, but as you said, they are still, they want to protect their IP, but for the startups, they have to start using OSAT so that they can do the true turnkey down the road. Yeah, but that's a great question.
Thank you, Mr. Dhiraj. For the companies in the United States, for many years, you have been working with OSATs in Thailand, like Fabrinator Focus, or in Europe, like Fix. You have Silitronics in the United States, allowing you to keep the supply chain and the manufacturing in the country. Dhiraj, it is great to have you on board. Let's continue, but now let's go back to the Foundry. Vikas, I hope the connection now is stable enough and we can finish your presentation understanding the Foundry view on the silicon photonics for AI. Vikas, let's try again. The floor and the attention of everyone goes back to you.
Okay, thank you. I apologize. I lost internet. I'm going to turn off my video because I'm on my phone. Hopefully, y'all can hear me. And I'm going to present. Start full. Yeah. Share. Okay. Can everybody see?
Yes, please go to presentation mode.
Yeah. And display settings. Swap. Okay, I apologize. So as I was mentioning, this presentation is going to be talking about the Foundry and the ecosystem. What I'm going to start off with, just giving you a brief overview of GF Photonics as a technology. And then I want to say a few words on the ecosystem, the work that GlobalFoundries as a company is doing, but then also, in the industry demands with respect to the ecosystem. So let me just start from the beginning. GF offers a silicon photonics technology that is sort of keyed towards, generative AI. As these generative AI systems are becoming more and more complex, so is the need for sort of low loss, high-speed communication, energy-efficient communication between the compute clusters. And towards that, GF offers this GF photonics technology. What it does, you can think of it as a sort of a system on a chip where we integrate, the electronics, at least the analog electronics, with the photonics. So you can see in this top sort of cross-section on the left, I have represented the electronics with the NFET and the PFET. But then in addition to that, there is a very rich feature-rich sort of offering with respect to photonic components, which includes active components such as the modulator and detector. On the right, there are passive components such as multiple options in terms of waveguides, silicon and silicon nitride. And we also offer high efficiency heaters with the sealed undercut. In addition to this, for light in and light out, a plan of record is this V-group based fiber connector. And for light in, we are also working towards an on-die laser. Now, all of this is integrated on a 300 millimeter wafer. Now, in addition to sort of the technology piece of things, we've also paid a lot of attention towards the packaging aspect. So we are working towards copper pillars and TSVs, and I will go into some of the details later on in the presentation. In addition to that, from a testability perspective, at least for the component level test, the device level test, we also have wafer level test capability. Now, the beauty, or at least the approach that GF has taken with respect to silicon photonics, is that we want to create a platform that is flexible, it's feature rich, and it allows for multiple architectures to coexist. So you could have different customers coming in with different circuit architectures or system architectures, and we are able to support that with this GF photonics platform. So on the left, I'm showing you on this slide, I'm showing you all just two sort of architectural options. On the left is the fast and narrow, which is the electrical switching scaling, and on the right, which is the optical scaling. And what that means is, in terms of fast and narrow, you can think about a narrow stream of electrical data, which is modulated using a ring modulator, and the electrical signal is imprinted on the laser output and output through a fiber at 100 gigabits per second. Now, on the slow and wide side, you can think of it as, a parallel stream of, lower speed electrical signals coming in. These electrical signals are muxed and imprinted on multiple wavelengths of light, and they are multiplexed into a fiber to give you sort of the same high-speed output. Now, the beauty of GF photonics as a technology is that both of these architectures can be made using the standard PDK that GF offers, and there's enough flexibility built into the process to allow for both of these architectures. So with that, I want to sort of just change tacks and start talking a bit about the work that GF is doing in terms of the ecosystem. So just as a definition of the ecosystem, it requires, it's a complicated system. It requires multiple companies to work with each other. Each company has a specialty. They are focused on a particular part of the ecosystem, but there's a high level of interdependency between these components. So if you think of it, starting with the fabless companies in the middle, we need EDA tools to be able to design components, a foundry to be able to produce. And then I've also added in this sort of electronic photonic IP ecosystem, which is very nascent for silicon photonics, but is also starting to grow. In addition, we just heard from an OSAT partner. We're going to be hearing from test. And then there's, the suppliers who provide things like lasers, fibers, interposers, and things like that. So all of these sort of pieces of the ecosystem have to come together in in sort of getting silicon photonics to fulfill sort of the full benefit of the technology. So starting off with the EDA ecosystem, GlobalFoundries as a company has been working with sort of the leading or the name brand EDA tool vendors, starting with ANSYS, Cadence, Siemens, and Synopsys. There are certain components that GlobalFoundries provides, such as the P-cells, the design rules, and the models, but all of the other infrastructure to allow our customers to design and get things first time right are provided by these EDA vendors. And it is important for these EDA vendors to get the tools right to allow for the ease of design and the flexibility that customers need. And as silicon photonics develops, there will be more and more integration of these circuits on a single chip. And so the complexity of these tools is expected to grow along with this technology. So this is just a view of, what GF offers as a company. There's a very large feature-rich library that we offer of passive and active components, with the intention of our customers getting first time right, but then also the ease of designing to this technology. And photonics does bring sort of differences from an CMOS and an electrical PDK, in that you have curvilinear shapes, and there are a lot of second order effects that were not present in electronics that need to be accounted for, such as sort of the nonlinear behavior of components under high power lasers. All of these are, of course, comprehended as part of the PDK, and we're working very closely with the EDA tool vendors to make sure that all of these sort of features are captured in the PDKs that we offer. Now, I found this sort of slide searching the internet. It is from Cadence, but it also gives sort of a good segue into where does EDA stop and where does packaging start. And what it's showing is the complexity of design as these technologies are progressing. While this is talking about more of CMOS, but I'll put it in context of the photonic side. So you can see with every generation, as things have progressed on the CMOS side, there is more and more simulation and look ahead and tool complexity that has come into play as part of the EDA ecosystem. And you can see this is sort of where we are right now. It talks about heterogeneous systems, and now you need to start comprehending system level, functional, timing, power, reliability, thermal, mechanical, and in the case of silicon photonics, also optical performance. And this is where things start getting complex because EDA needs to not only comprehend the circuit, but also start comprehending the systems. Now, what I've drawn here is sort of just to give a flavor of the complexity of the packaging ecosystem that has come into play for silicon photonics. So what I'm showing you is sort of three forms of packaging: one on the silicon bridge, one on a silicon interposer, and one on a multi-chip module, an organic laminate. And once you start considering the options of these packaging sort of choices and the corresponding components, packaging components that go into it. So for example, there are multiple solutions for fiber attach. Once you start thinking about silicon bridge versus interposer, you may have mixed pitch versus very minute bumps. You need to account for the electrical IC attached to the optical engine. And of course, things like thermal components, heat sinks, whether the components are lidded or unlidded. So this is sort of the ecosystem that we are operating in from a silicon photonics perspective. And one of the challenges is depending upon the solution, whether you approach it sort of bottoms up or tops down, you could reach very different sort of solutions. If you look at the ecosystem starting from the electronic or the photonic circuit, going up through the packaging, through the module build to a system build, there are certain criteria that come into play, whether you do it tops down or bottoms up. Starting from tops down, you have to think about power consumption, signal integrity, thermal profiles, whether you need a heat sink, cooling plate, the type of cooling that you require, whether it's liquid or air cooled. and reach of fibers, etc. But then if you look at it from bottoms up, you need to think about the bump pitch, whether it's mixed pitch or fixed pitch, the type of fiber attached that is required. And so one of the challenges in the industry, which the industry will soon need to deal with, is the fact that depending upon its bottoms up approach and tops down approach, there could be sort of a very large matrix of solutions. And that's the reason I'm glad the APC has sort of taken on this challenge on of getting us all together as sort of an ecosystem to talk about these challenges. So from a GF perspective, I would say, there are certain components that we are sort of prefetching as we know, as we talk to customers. And if you start looking through sort of the unit processes, whether it is copper pillar receive pads, TSVs through the copper pillar with copper pillar for sort of the next generation 3D packaging, passive fiber attach, and laser attach. These are components that we've already built into the GF Photonics technology, and we are continuing to work with our OSAT partners in order to put in the infrastructure to actually go to high volume manufacturing. The last slide I wanted to just talk about is sort of the nascent sort of photonic IP ecosystem that is just starting to burgeon up. So you can think, you sort of break up a chip, starting with an IP level, sort of a component level. Once you start putting multiple components together at a circuit level, and then once you start putting circuits together at a chiplet level. And I do believe that in order to take the full potential of this technology and sort of get it to a market and get it to people who are not necessarily photonics designers, you will start seeing a lot more of this sort of photonic IP ecosystem start burgeoning in this industry. And so in closing, I just wanted to sort of close with sort of two bullets. One is that GF Photonics as a technology from a foundry offering perspective. What we've taken the approach is we want to build a platform that is flexible enough to be able to support multiple solutions for interconnects, but then this sort of flexibility can be extended further into different markets also. So that's the approach that GF has taken. And part of that is also, as a foundry, we need to be able to scale it not only in terms of circuit solutions, but then also scale it in terms of volumes. And that's the approach that we have taken. And in order for silicon photonics as a technology to be sort of the vibrant and get to its full potential, we will need sort of the disparate people in the industry, the OSAT, the IP ecosystem, the EDA ecosystem, the test ecosystem, to all work together, and perhaps I'll use the word coherently, work together to be able to get this technology to its full potential. Thank you.
Thank you very much, Vikas, for a great presentation. It is a paradigm shift for us to have the GF Photonics PDK available for everyone, and I will encourage everyone to come back to you and to see how they can already start using this PDK. Is actually quite easy to access. I have just one quick question for you before we go to the next step. So
Sure.
One thing that for me is a challenge for silicon photonics today is the wafer level testing. So the company that is following the OSAT can have an easier way to serve their customers. What is the current status on wafer level testing? What is the current yield of silicon photonics? Can you comment on that?
Yeah, so I won't comment on yield. I think the yields are pretty high just because of the fact that photonic components in general tend to be large in terms of size. So in terms of defect limited yield, that's usually not an issue. I'll make a comment on the wafer level testing. Now, wafer level testing is just fundamental, and GF Photonics offers sort of two pieces of this sort of puzzle for wafer level testing. So the first thing is we do have, as I'd mentioned right at the beginning, we do have a capability that was developed internally at GF to do wafer level testing of components. It's called an inline optical test system. And what that does, it allows GF to be able to test components at wafer level and use the output of it to be able to create statistical plots of individual device components so that we can make sure that the customer understands that the wafer is healthy. Now, there is also this whole aspect of system level testing, at speed. And that is work that we are continuing to work with our test partners on. There is a lot of development that needs to be done, not only from test programs, but also fixtures. People are talking about periscope probes to be able to probe the edge of the wafer. So that ecosystem is something that needs to be developed. The other point that I do want to make is the fact that we integrate both electronics and photonics. One could conceive about, self-test because of the fact that the electronics is built on the same die as the photonics. One could conceive of self-test circuits which do not require an optical interface, that you can test everything, convert it into the electrical signals, and at least talk about self-test circuits. So that's sort of the approach that we've taken.
Thank you very much, Vikas. I think the world of self-testing on integrated photonics is a paradigm shift, and we are all very, very happy to see the foundries working on that. Let's continue. Let's go now to the contract manufacturer. Does everyone in the room know, and we have several hundreds of people in the room right now, does everyone in the room know that Jabil has 260,000 employees? This is one of the giants in our industry that has been developed contract manufacturing service in many different markets, but they are taking silicon photonics very seriously, as we all know after the news from Intel a few months ago. Noam, Ophir, thank you very much for being with us. Thank you for representing Jabil, and thank you for taking the supply chain role of contract manufacturing. The floor and the attention of everyone is yours.
Thank you, Jose, and thank you everybody for listening in. My name is Noam Ophir, and I'm a Senior Technical Director, OSAT and Silicon Photonics at Jabil Cloud. I'll talk a bit about our view and mostly observations on volume scaling of silicon photonics and the ecosystem, as Vikas termed it. So let's go ahead. So just for those who are not very familiar with Jabil, Jabil has been around for nearly 60 years, as you said, Jose. More than 250,000 employees, more than 100 manufacturing sites across the globe. And in fiscal year 2023, we had a revenue of 34.7 billion. And just recently, we re-entered the S&P 500. In terms of our solutions, and this roughly lines up to Jabil's divisions, we are engaged in all of these end markets. And we need to keep in mind that, yes, in this conversation, we're talking very much about AI and machine learning, which maps into cloud, but actually underlying technologies and capabilities will develop in this field are all also maybe applicable to other end markets such as automotive, healthcare, etc. Next slide. So specifically for focusing on the AI ML, Jabil Cloud is a footprint in the service space with white box hardware volume deployed to hyperscalers and other clients required tailored solutions for their data center needs. And Jabil is engaged across all aspects of hyperscaler data centers, from compute to networking, as well as power, cooling. And we see integrated optics being critical to AI ML platforms sooner rather than later. In general, AI ML, as our clients are telling us, are driving a lot of technologies which have existed perhaps for a while, but have not been adopted, such as liquid cooling and silicon photonics, and really becoming a forcing function to introduce these now. And Jabil is now getting more and more involved in silicon photonics because our clients are asking us to be in this, and it's business impacting. Specifically in silicon photonics, our clients are asking us to assist with verticalization, simplifying supply chains, and also accelerate the technology adoption to enable high volume manufacturing at the cost targets that are needed. So some observation on the silicon photonics manufacturing ecosystem, and this is kind of an example flow, and there are many other flows that exist, but this is one for how a transceiver could be built. So on the top left, there's wafer fab, for instance, GlobalFoundries. There'll be wafer test. Some clients will not do it at the fab, could be that they own it domestically or internally. Then if this is a chip that needs to be bumped, to get it bumped, might be something you now need to find a partner that's yet a different place. Then to singulate and dice might yet be another place. if you're doing some bumping and you're doing flip chip assembly to create a multi-chip module, that might be yet another vendor or stop across the globe. And then you get to fiber attach, lid attach, EO test, and then finally actually build it into a transceiver model. So we have this multi-hop supply chain, and our view is that there's no one-stop shop for everything right now, and it's exacerbated by the multitude of existing packaging schemes that are really driven by the optical I/O constraints. And what this means is that essentially yield, cost, and time to manufacture are relatively high right now, and our clients are eager to simplify this process. But so far, I think we as the industry have not really stepped up to deliver this. One of the issues I said was the plethora of packaging. And specifically, if you look at the optical packaging, I have here a few examples of interesting solutions. V groups from GlobalFoundries, Nubis Communications with a vertical solution, and detachable connectors from Terramount. But there are many more solutions right now in the market being productized. And the problem is that when we have all these different technologies and no standardization, is that it makes it hard for CMs to commit ahead in terms of capital investments. So it's not just the fiber attached machine itself, but rather that these different optical I/O schemes also impact the rest of the processing and package design on the electrical side. So the optical side really dictates a lot of the package flow for everything else, and the fragility of it drives the sequences, especially with optical epoxies and fibers, allowing you a limited thermal budget, and the fiber handling complicating as well automation and handling. So in different slides, there's always this exponential growth. And in different years, if you look at the historical forecast, it was always imminent, this exponential growth, where we'll transition to a high volume regime. In the past, large OSATs have been burned with investments that did not translate into volumes, as this hockey stick behavior did not materialize at the timing that was forecasted. But we believe that the inflection point is near and currently held back more by the manufacturing ecosystem, which has not geared itself to be able to deliver at the speed at cost targets rather than market demand. But there is a chicken and egg type of situation we're facing, that volume orders are waiting for the appropriate supply chain solution that can deliver at the cost and volume targets. But building up the capacity requires a significant investment upfront, which is at high risk if it doesn't materialize. So, and it's difficult to do a gradual build for high volume manufacture, as the cost target is only realizable when you put high volume tooling on. In terms of another observation that I like to make is that there's this blurring of perhaps traditional roles on the interface between the foundry and the OSAT. We observe that because of all the custom needs of silicon photonics, foundries are forced to hold the hands of their clients beyond wafer fab into far back end of line and post-processing. And in absence of significant silicon photonic volumes, large OSATs may not be incentivized to make significant efforts into custom solutions that address silicon photonic wafers. So that's one area of blurring of the line where the fab and the OSAT blurs. On the other side, because of fiber handling and because of the sequencing of integration, the line between CM and OSAT also is blurred on the electrical assembly and the optical assembly. So we're seeing this blurriness of lines, and we need to figure out as an industry how we provide a service that our clients can now scale with. Jabil has a track record in integrated optics since the acquisition of AOC Technologies back in 2015, and followed with manufacturing ramp of silicon photonic coherent optical engines, and a presence that's now expanded with the acquisitions of the Intel transceiver business. We think we have the scale in the global footprint to chase down service intimacy and simplify supply chains. We believe we can assist this standardization and participate in supply chain simplification to unlock the velocity of silicon photonic technology adoption. In our view, partnerships can be a path forwards to advance the integrated optics ecosystem. And we're engaged in some of these discussions in industry, and we look to further engage in more discussions as this topic continues to evolve. So my final words would be that we look forward to hearing what other players' views are, and to further this discussion at the OFC panel.
Thank you very much,
so much.
Noam. I really appreciate when you come with your doubts about the volume needs, because of course, Jabil is the manufacturer of the GoPro camera, it's the manufacturer of many components in everybody's mobile phones, and you are thinking now silicon photonics will have their needs. My question to you is, because honestly, I have no doubt that we will have demands on volume production of silicon photonics. My question to you is everything else ready on the contract manufacturing? I mean, the micro lenses, the chips, the electronic chips, the packaging, the volume production, the equipment necessary, is everything else ready? Should the big customers, should the consumer companies come to you with demands of silicon photonics?
Well, the consumers are coming us with demands, our end clients, but there's still a process to establish the volume, and Jabil has already a presence in volume now with silicon photonics and in other products. But yeah, there's more work to be done, and there are areas in the intersections between OSAT and CM that we need to figure out exactly how we do it. So
and to do it, you need automation. To do the volume production of silicon photonics, you need equipment that can provide automation on the assembly, packaging, and test. That's why the next speaker is a good friend of yours and a good friend of mine. We go all the way to Aachen, to Bremen, to Germany, to meet Torsten Varenkamp, the CEO of one of the most beautiful success stories in the photonic industry. For those of you who want to know the story, Google Torsten Varenkamp, Jose Pozo, and read the article. It's a beautiful story. But now we are talking about what Ficontec can do for the contract manufacturer and the OSATs. The floor and the attention goes to you, Torsten.
Thank you, Jose. You can see my presentation, yeah?
Gorilla Glass Clear.
I would like to thank you, the previous speakers, for these excellent talks, and a lot of points were raised by GlobalFoundries, Silitronics, and Jabil. What I might tackle now in my presentation. My name is Torsten Varenkamp. I'm CEO and one of the founders of Ficontec. Ficontec stands for Fiber Connecting Technology. So that is one of the key ingredients of the topic we are talking about. Even though we're talking about today about the AI revolution, the topic is much broader than just AI. So photonics today is everywhere, and as we heard in Jabil, we see the same things. It's not only telecom, datacom. It's LiDAR, it's biosensing, it's quantum technologies, much more areas where photonics today is key for the future. And a lot of these areas have PICs inside today. So and we, as an equipment manufacturer, where I will give the view today, are seeing these PICs now implemented in all these devices. Very challenging components and structures we see, all different types, no standardization. And that is what we have to work and live with as an equipment manufacturer. If you see the product assembly, and I'm just touching the areas we see. There's many more areas, the whole electronics assembly, what you have to tackle. We have to start with a known good die in the components, the integrated photonic devices. So we are in need, and the previous speakers have touched that, we are in need for electro-optical wafer level testing. So we need to integrate the laser source, as we heard previously. So we need high precision die bonding systems, which bring the integrated, which brings the laser into the integrated circuit. We need fiber array and assembly and alignment tools and equipment, which is producing the fiber studs themselves. So we need fiber interconnect technology. And finally, in order to really enable our volume production, we need reliable machines which are potentially also work in line, as is today totally common in electronics assembly. So I will touch these topics, and I will start with the wafer level testing. And I will all touch this very briefly because about every item you can give a whole speech itself. So if I look at the electro-optical wafer level testing, we have two main topics we need to tackle. So there's grating coupling we have to enable, or we have edge coupling devices on wafer level, which we have to, as equipment manufacturer, we have to generate. For this edge coupling specifically, and it was also raised before, there's these little periscopes which were developed by a company called Vanguard Automation. These units we are using in our wafer testers, and these little periscopes, super small, highly efficient, and you can print them onto the fiber array, and you actually dive them into the wafer, in the trenches, and do edge coupling. So perfect working technology. We build a lot of wafer level test systems which have this capability, and it's working fully automatic, and also very short coupling times. So that is the technology which we see a lot right now implemented into the industry. This is such a machine, how it looks like today, one of the tools we developed. So generally there's a wafer table, which is usually 300 millimeter, heatable and coolable. Then there's the optical alignment engines. So there's usually two 6-axis alignment engines inside, which then come from the top or from the bottom. That is a new system we're currently developing. So electrical probing from the top, optical probing from the bottom. So there's technology which is developed for different type of devices. But there's much more than just the wafer table and the optical interconnects which need to be taken care of. There's for sure the high throughput requirements we need to see. There's short alignment times, and the customers want to have each die 100% tested in very short time. Then we need to have interaction with the instrumentation company. So like Quantifi Photonics as the next talk. So we have actually the whole range of Quantifi Photonics products already as part of our libraries in our machines. There's RF requirements we have to tackle, so up to 65 gigahertz, which we need to tackle. The whole data handling needs to be done automatically. So you need to operate this machines as slave or as a master. So sometimes the optical test equipment is driving the machine. So all these things we need to take care of. There's much more to say about wafer level testing, but there's, as I mentioned already, there's a lot of assembly requirements we need to tackle as an equipment manufacturer. So there's a need for high precision die bonding, and what we developed for that is pretty much an infrared viewing system where we can look through the silicon wafer, and we look from the bottom through that device using infrared light and infrared cameras, and that allows us to see if I have a die above the silicon wafer, I can see from the bottom side the alignment structures on the chip. And while doing that, I can do the alignment. So I can do an XY manipulation, can see the die above the wafer, and finally I can combine that with a laser bonding process. So I have a little video how that can and how it's actually looking. So you see the little die on the pickup tool. You have the optical component or the silicon device on the bottom side. You bring the die above the silicon component. You see the solder in green. Now I switch to the IR camera for the bottom side, and you see the die manipulated above the silicon component. So you see the waveguides, you see the alignment marks. I bring them all into alignment. I bring them into the right position. And finally, after I did the alignment, I can start the bonding process. And I do that potentially through the same optics, or I can switch optics and have the laser doing the bonding process. So that's our approach to a very high precision alignment. We have some alignment results. Actually, we reach approximately plus minus 200 nanometer 3 sigma alignment accuracy. And for us, that is then combined with the localized through silicon laser soldering process. So shooting with a laser from the bottom side through the silicon wafer to solder or to heat the solder and get the soldering done. And this is what we are currently working on to do this whole thing also wafer level based. That is something which we will finish most probably early end of Q1 or early Q2. So that's what's cooking in our lab right now. So very happy about the results so far. But the next step is not only the die needs to be assembled, one of the most critical parts, and this is what is also manifested in our name, the fibers need to be connected. So that fiber connecting technologies, that's a key part we are dealing with. That is our bread and butter business. And that we can align fibers passively and actively. Most of people know we have 1,200 machines in the field which are somehow related with fibers and optical assembly. But what's new is really the generation of the whole fiber studs. So that's what we are currently working on, a full automatic process to generate these fiber units, stripping, cleaving automatically, putting the fiber ribbons and the singulated fibers into the connectors. So that is one of the, because it's flexible devices, a very challenging task, which need to be handled fully automatic without any operator intervention. But one of the key ingredients for that is the fiber strip and cleave process. That's what I'm showing here right now. So it's actually the stripping of a fiber ribbon, and finally the cleaving process of the ribbon, which is done completely with a laser, and then finally the implementation of the fiber ribbon into the connector. And so currently we're working on a process where we build the whole fiber stud fully automatic. And within the next, I would say 4 or 5 months, I will be able to show a complete real video of the complete machine. That's what is right now in assembly. So talking about these different processes, all these are singulated machines, but what's important for us, and this, as I said, it's very common in the electronics industry to generate these in lines. So, and this will be for sure not only Ficontec machines, there will be many other machines which will go into these inline systems. There will be wire bonders, there will be die bonders of other manufacturers. There will be the fiber attached systems. So, but this is not for the AI world, but for other customers. We have generated photonic assembly process already in line. This, for example, the air purity sensor here for German tier 1. Very sophisticated lines with multiple active alignment processes, with full automatic feeding systems, with end-of-line testing inside this line, with laser marking at the end, where your data matrix code is already printed on the device. And then finally, the final component goes out of the end feeder in blisters. So, and we envision that for also transceivers in future. On the right side, the picture, you see a clean room in a mass manufacturing contract manufacturer in Thailand. There's 150 machines in that bay, which is like cassette to cassette handling. That's mainly for lens attach, for fiber attach to the RX side, TX side. So all these things are completely automated. But in this case, you have operators handling cassettes from one machine to the other with cure processes in between. Also that, and I agree with the previous speakers, there's a lot to be done as a community in order to get that full automatic and high volume manufacturable, if you really target the quantities we talked about previously. So we are working on machine learning for these kind of processes. When you want to go high volume, you need to make sure your KPIs are tracked. You track the yields. These yields of these machines are running over 99.5% yields. We have we need to have high uptimes. We need to have a preventive maintenance. So if there's something going into the wrong way inside this machine, you want to know that before the machine goes down. So there's AI processes monitoring certain process steps, and also process optimization is done with the help of AI today. So we have a group working in our R&D department. We have implemented the first these kind of things on the first customer sites. There's edge computers inside the machine, and then they report to a so-called revision control service, where we can control up to 200 machines with the so-called copy exact processes, that when you want to roll out a new process parameter to the machines, you can do that with one click. You don't have to run from machine to machine and do that. You can do that inside this revision control servers, and this revision control server, they will roll out a new process to all the machines. So there's a lot of things happening which will allow high volume manufacturing, but there's still a huge amount of work to be done. So we see there's required some solutions for wafer level testing, high precision die bonding, fiber interconnects, and at the end we want to bring all of this together in lines. So that's what we are working on. And as a conclusion, so assembly and test are and will remain cost drivers for the photonic products. We have automated assembly steps for most of the process steps necessary. And the last decade was pretty much doing this in individual machines, but we see the next decade now coming to do that is a very high level of automation. As the previous speakers said, that's a key, and the necessary steps in order to really be mass manufacturing, generate high volume manufacturing. Thank you very much.
Thank you very much, Torsten. Thank you for a very inspiring presentation and for continuing being the success story on the automation for manufacturing and test. You made a very strong impact on the assembly, but at the end of the last slide, you said both assembly and test remain the need. When it comes to automation for the test and wafer level testing, what keeps you awake at night?
Yelling customers? No, but what keeps me awake at night is really the large variation of components we see today. So there's no standards. There's every single thing we see, every single customer comes to us, every CM talks to us. it looks always different. And this is something which, I mean, finally, I always say that we live from customization, but it also makes the process of being compatible to high volume manufacturing very difficult.
You know what keeps me awake at night is that for me, there is always, whenever we discuss this, people say there is a difference between test and characterization. And I believe that currently customers require volume characterization. They don't require volume testing. They really want to know the performance of every modulator, of every integrated laser, of every integrated detector, down to the quantum efficiency. And for that, making this volume characterization is the next big thing. So Torsten, I'm going to introduce now one of your partners. The first time I met the next speaker, the first time I met the next company, Quantifi Photonics, I met them because their equipment was at a Ficontec machine. And I fell in love with what they can do. Kees, Propstra, thank you very much for being our next speaker today. Tell us how Quantifi Photonics works with Ficontec to satisfy the need of Jabil, GlobalFoundries, and any other company in the ecosystem. The floor and the attention of everyone goes to you.
All right, good day, everybody. Let me make sure that can everybody see my slides?
Crystal clear.
All right, perfect. So thank you very much. So first of all, I would like to thank Optica and APC for organizing this event. This event really provides a unique perspective, a very broad ecosystem perspective of multiple partners across the ecosystem, from foundry all the way to end user and everything in between. And why is that so important? Noam showed a very nice graph with the question marks. So where is that inflection point? I truly believe that 2024 represents this inflection point. You know, the technologies are pretty mature, but we still need to scale them to high volumes. And everybody is now preparing to be able to scale these integrated photonics technologies to high volume. So that's, I think, is very important. So if you look at our industry, obviously AI is really driving a lot of this. We've seen a lot of plots where you compare the data requirements for for AI, you compare it to Moore's law, and you see there's a huge disconnect. So all this data that is required for AI and artificial intelligence, move the data around. You need to have these very high density, high channel count, high throughput optical interconnects that are based on integrated photonics, on silicon photonics. And to my presentation, really focus on the testing perspective on scaling these technologies to high volumes. So what is really the problem statement? And we've seen it, you start with a kind of a wafer-based, product, and you need to then cut it into multiple individual dies. Then you start kind of the assembly process. You combine it with the fiber array, other components, kind of create an optical subassembly, and then you combine it with PCB, electronics, and so on into a module, a kind of a packaged product. And of course, you go through the product life cycle where you start in R&D, then you have the validation and manufacturing, and the test requirements are really going to change throughout those cycles. So it's really important to pay attention to that and to develop the right kind of testing strategy to be able to do that successfully. So if you look at these optical interconnects, they really consist of a bunch of photonic devices. So you have lasers, modulators, WDM components on one side, then you have the waveguides, the receivers, the grading couplers, and combined that creates the high-speed optical interconnects. But of course, these different photonic devices need different methods to characterize it and to determine whether they're working properly or not. So that's the challenge on one side. So a lot of different devices, a lot of different characterization methods. And then if you look at the measurement overviews, you have a bunch of different things which are really quite unique. On one side, you have just pure passive measurements. You just do kind of a polarization wavelength scan of a passive waveguide or just a WDM component to see how it behaves. But then you have active tests. You power the device, you control the device, you provide some kind of a bias. For instance, you power up the laser diode. What does the spectrum look like? Is the side mode suppression ratio, is it sufficient? Is it meeting the spec? What kind of if you look at the modulation depth of your modulator, you want to characterize the sensitivity of your receiver. So those are active devices. It's a little bit more complex. You need to power, you need to hook up to your device. And then you have the high speed measurement. So that really gives you the full bandwidth characterization of your device, really for its intended high speed operation mode. So it's like eye diagrams, transmitter characterization, bit error rates, or receiver sensitivity, or even more exciting is to do a full S parameter characterization to see what kind of bandwidth does your transmitter, your receiver, or the whole system have. So obviously those different categories will make it a little bit more complex. So luckily we have a lot of solutions for that. So if you look at the wide variety of instruments available today, you can break it down in categories, like you have on the input side, really controlling the light. You have a laser polarization controller, different types to bring the light into the device. Then on the other side, you have characterization instruments to measure the light, whether it's power levels, optical spectrum, or bring it in the electrical domain, or do kind of oscilloscope measurements, or kind of a photocurrent meter. And then you have measurement tools that are really having an input and an output, like for instance, a light wave component analyzer, which is basically an optical vector network analyzer, so you can really measure the bandwidth of your device under test. Or you have a bird driving a high-speed data signal into the device and see what the response is. And you have a lot of support modules to kind of optimize the conditions. So optical amplifiers provide really high levels of optical signals if you need it. Optical attenuators to really control the power level, to do, let's say, kind of receiver sensitivity measurements, switcher splitters, but also very importantly, standard equipment like SMUs to measure and drive the device under test, or electrical vector signal analyzers to do kind of spectrum analysis and things like that. So, it's a very complex view on how to characterize the devices, but the solutions are there, and now we need to just really strategize on how to do that. So now the question is, what are you going to test, and when are you going to test it? So we go through this cycle from wafer to die assembly and module. Where are you going to test? So obviously, if you wait too long, you're going to be potentially wasting resources and materials. So you probably want to test a little bit earlier, making sure that you have a known good die. And especially with, let's say, the state of the industry, it's pretty mature, but the yields are still relatively low. So you probably want to test a little bit more earlier in the process, so that maybe at the wafer level, you determine this is my known good die before you commit to all the next stages. So going into a little bit more detail, so wafer level testing, so that's a very important stage of this process, and a lot of people are asking questions about it. So of course, what you do is this is a pretty complex setup. You have a wafer handler, you need to have a probing system, optical as well as electrical. So you inject the signal into the wafer, you power and activate the devices, you measure the optical signal, and you probably want to do a lot of characterization. So one challenge here is, and we'll probably talk a little bit more about it, how do you connect to the wafer optically? There's a lot of different ways. There's not too much standardization, but I think we're making a lot of good progress. A lot of very viable solutions can do this fast without too much active alignment. But really what we're hearing from the industry, that at this stage, a lot of folks want to do very detailed characterization, including some of the high speed measurements, really to make sure that you select the die as known good die to basically advance in the manufacturing process. And in the first phase, kind of the pre-production, the first phase of the ramp, you probably want to do as much as possible. Hopefully then when you really go to high volume, you have more data so that you can say like, well, we can reduce the test coverage and also maybe reduce the percentage of devices tested, but you really need to have the data. So really, front load the testing in your product life cycle, in your manufacturing stages, based on which you can make decisions to, at some point when you go to really high volumes, to reduce the amount of testing. So then the next step is really, you have the known good die from the previous stage. Now you need to do the fiber array alignment and maybe some additional assembly steps. Now this is hopefully relatively high yield, relatively low risk. So you do the alignment, you want to make sure that you have the optimum alignment. Of course, you test that. And then, maybe as to be on the safe side, you want to validate that all the channels are still working. So maybe a quick scan that all the channels are still alive, because you know that the device is working well from the previous stage. And that would be, kind of a reasonable justification to limit the amount of testing. However, if the assembly steps are a little bit higher risk, you may want to add some additional testing to make sure that you didn't break the the device on the test in this stage. And then if you look at the kind of the final stage of the manufacturing cycle, so you take the optical subassembly, you combine it with the PCB, some of the electrical ICs, and maybe some other things into kind of the form factor, the desired form factor. No, it's really critical here. This is the last stage before you send it out to the end user. So you really need to make sure that it meets all the performance requirements. So you really want to test that initially, probably even over temperature, just to make sure that it really meets all the requirements. And then again, once you collect more data, you have a little bit of a guard band for the thermal behavior. You can scale down the testing to minimize it, but still there's a lot of testing involved. And it seems that you can optimize the testing, but there's probably still a fair amount of 100% testing required. Like every channel, you need to make sure that it is working at high speed. So it seems right now that it's still desirable to do high-speed testing for all the channels. That means that there is really a need to parallelize the testing as much as possible to have an optimum test flow and manufacturing flow to be able to test these devices and make sure that they are 100% working before they go being deployed in the field. So in conclusion, what is a successful testing strategy? You need to make sure that you have all these test functions to be able to characterize it. It needs to be flexible because you go to you transition from different stages, product life cycle, manufacturing cycle. It needs to be integrated into the probing and assembly equipment, very important. Scalable to high channel count and parallel testing. High density because you need to do a lot of testing. You need to integrate it into these machines so that you don't want to take up too much space. That's pricey. And of course, optimize test flow to really test your device as quickly as possible. So what are the asks for the ecosystems? Why do we need to cooperate? And this has already been mentioned by some of the other partners is, what kind of standardization do we need to have, like optical signal access? It's not trivial. It's not just like electronics. It's a little bit more complicated. Are we going to standardize on that? The measurements and the test plan, it seems that we're kind of converging on something, and which is really powerful so that we know exactly what needs to be tested and when. And then, maybe some thoughts like, do you want to have a standardized industry hardware framework that has certain mechanical, dimensions, just kind of a modular approach, something like PXI, where you have, hardware triggers, so you can really optimize your test flow, and also maybe a kind of a software framework where you have, kind of an API structure, but maybe a kind of a modern version of Skippy like gRPC to make the test flow, as optimum as possible. So this kind of concludes my presentation on a testing perspective on scaling integrated photonics technologies.
Thank you very much, Kees. I can tell you, AI is changing the game. Right now, AI is changing the game. Actually, last year at OFC, we had Agile Labs talking to us about 4 terabit per second WDM needed for AI. at the PEC Summit last October, we have NVIDIA telling us about multi-terabit per second. The high speeds are crazy. How is Quantifi strategizing towards offering the testing solutions that the AI is going to need today?
Yeah, it's a great question. I mean, right now, what we're seeing is that there's still a lot of technology at 100G per channel that is going to be scaled in the next couple of years, and of course, then the next wave is going to be 200G per channel. We are actually developing solutions to be able to align very well with that kind of technology roadmap. So very important, But again, 100G is probably going to be the first phase. Really scaling in the next couple of years, and then 200G maybe a few years later.
I would like to now continue with the program to link all this ecosystem to one company who really has put their money where the mouth is. We go to Broadcom. In September, there was this big press release with Broadcom talking to Google Cloud towards generating an ecosystem for generative AI. And they need a physical layer. They need to support a technology that will enable AI in the future. For that, we have Manish Mehta with us from Broadcom to close the meeting the way that it is. Manish, before I give you the floor, one thing for everybody in the room. If you have questions for Manish or for any other one of the other speakers, now it is a time to put them in the Q&A section. Press the Q&A button and write your question there. After Manish's presentation, we'll have our Q&A, which is, of course, for me, the most exciting part of the meeting. But now we go to Broadcom. Manish, the floor at the attention of everyone is yours.
Thank you, Jose. And can you hear me clearly and see the slides?
Loud and clear.
Okay, great. So first of all, I want to thank APC and want to thank Jose for putting on this session, and Happy New Year to everyone. I think at Broadcom, we've been quite public about our CPO investments for the last several years. I'll share some of our technical progress and share some thoughts on ecosystem development towards the end of the presentation. So this is a slide that I think many of you have probably seen before, or at least a similar version. And at Broadcom, we focused our silicon photonics investment on co-packaged optics, initially targeting to pair our optical engines with Broadcom core silicon for networking applications. And the target value proposition is well known: lower cost and lower power compared to traditional optical interconnects. And ultimately, we believe delivering silicon level reliability. The graphic on the right shows our estimates for the power benefit against other optical interconnect solutions today for networking, where we expect the co-packaged optics to deliver a 60 to 70% reduction compared to traditional optics. And this slide just visualizes the migration. Of course, I'm sure many of you are aware of traditional optics to co-packaged optics. The left side shows an explosion of one of our standard single mode 4-channel modules. And while this paradigm is deployed widely in the industry for more than 20 years, it is discrete, it's manual labor intensive, and the industry has made pretty great strides in the last 7 to 8 years, progressing to what you see in the middle, ramping silicon photonics. However, it has been predominantly with low density optical engines used in transceivers, either 4-channel and more recently 8-channel devices using silicon photonics. So our goal is to now take that one step further, increase the integration density by an order of magnitude, and then use advanced semiconductor packaging to co-package the optics on a common substrate with core networking ASICs. So, of course, there are many ways to approach the problems, and there are many solutions that different companies and industry can and should try. Innovation in this space does need to run in parallel by various parties. Some of the areas that we focused on our first CPO program that we called Humboldt was to develop optical engines with 32-channel photonic circuit die bonded to 32-channel electrical circuit die. The electrical circuit die have our modulator drivers for the TX path and TIAs for the RX path. We also developed a detachable optical fiber connection at the optical engine interface in order to facilitate a soldered optical attach to the substrate, and we are soldered attach of the optical engine to the substrate. And we also worked pretty early on with ODM partners to test system integration in a chassis manufacturing environment. So here, this shows, an example of the results of one of our solutions. The left picture shows a standard switch, which is populated by a large number, say 32 to 128 optical transceivers. The high-speed signals propagate from the core ASIC through the host PCB in the box to the optical transceivers. Whereas the right picture shows our Humboldt CPO SVK system, the validation vehicle we built. And this system was a half CPO and half pluggable, but you can see the implementation of the CPO section where the high-speed signals propagate from the core ASIC to the faceplate over fiber. And then this, is an example of what that half CPO, half pluggable implementation looks like in an ODM box on the front panel. The top section shows the CPO with fiber IO ports and remote laser module pluggables on the edges. And the bottom shows the standard pluggable section. And you can kind of visually see how moving to CPO from a standard pluggable gives pretty significant faceplate savings. In this case, it's about 30% additional faceplate area for ventilation. That does offer some pretty interesting system design opportunities. And wanted to share, won't go into too much detail here, but wanted to share some results from our early production builds. These are not one-off builds, these are multiple lots, multiple devices in a lot that we have run through manufacturing processes. I think we've been able to get to consistency on optical engine performance from run to run. And if you look at the bottom right plot, this was our first generation silicon germanium based device where we did have worst case power that was under 8 watts in full system operation, 8 watts per 800 gig for the optical interconnect. We do expect that to come down further on the most recent devices that we're building, which are based on CMOS implementations. So now I do think, aside from all of the upstream challenges that certainly exist in developing and deploying highly integrated silicon photonics, there has also been a lot of fear in the industry on what it would be like to assemble, bring up, and deploy a CPO system in a network, since that architecture is so new for optics. And honestly, it was pretty scary for us as well early on. It took us 3 months to bring up the CPOs in a system the first time that we had a successful installation. Within a year, we had been able to reduce that bring up time to about 2 weeks, which was a significant improvement, but still nowhere near acceptable for scale deployment. And then it took another 6 months after that to where we could bring up a system within a day. But of course, now that we've gone through that experience and gone through that learning curve, we feel like that's something that is no longer, we'll be able to more quickly get to those shorter time cycles. So, we continue to make progress on our programs. We've got a good base of customers, both system integrators and end users, planning deployments. But there are some areas of industry collaboration that can accelerate time to high volume from our perspective. I'll share some of those thoughts in the next few slides. These are some images that illustrate the optical path of the types of systems that we're developing. And we start with an optical engine. You can see a cartoon on top that has our PIC and our EIC. We connect them using fan-out wafer level processing, or FOWLP, which is a highly integrated advanced packaging technique deployed, which is critical for the type of density of integration and bumps that we need, or connections that we need between the two chips. And then we bond these engines to a common substrate with our core ASIC. Within the box, the optical engines route to both the front panel I/O ports and remote laser module optical connectors. Now, we've been targeting networking deployments, but one place that I think would be good to begin revisiting commonality is what's actually progressing down the fiber. We are progressing in the industry right now in a direction where compute applications and networking applications will require very different wavelength plans, and because of that, integration schemes. And I do think there's important discussion needed on whether the application scenarios that are driving this variation are strong enough to support fragmentation. Because again, there's a broadly deployed base of kind of parallel single mode, 4-channel, 4-wavelength solutions that for networking, or even a lot of the emerging AI applications, which are still highly networking oriented, can continue to progress down this path, moving from 100 gig to 200 gig per lane speeds. We've also described a fair amount in the past about our remote laser module design. Now, frankly, we were already progressing quickly when the ELSFP standard was emerging, and our focus at the time was to deliver remote laser modules with uncooled 20 dBm lasers. But the RLM is an important area of development in the industry. We'd like to see continued progress, increasing laser power and enabling either longer link budgets or higher split ratios, therefore reducing the amount of fiber within that's needed in a box. We are open to integrating our CPO solutions with various RLM designs and form factors. It does still feel early to decide on a single solution. We don't know, and I don't think the industry knows yet, whether the right optimization vectors are, say, cooled versus uncooled, or laser diode power versus quantity. But I think we're pretty confident and do believe that this is definitely a part of a CPO solution that will disaggregate and will will benefit from interoperability and more industry level collaboration. At the CPO or packaging level, we do hope to see more emphasis by foundries and OSATs, keeping photonics in mind during roadmap development to support both silicon photonics and CPO requirements. Some examples of that, double-side attach when you're using, say, PIC EIC bonding rather than monolithic solutions, so that you can take advantage of low speed, very, very advanced CMOS nodes, 5 and 7 nanometer for low power electronics, coupled with optimized, photonic circuits. You need to attach, on one side to a substrate or some type of package on the other side to the other device. And that double-side attach is often unique relative to standard electronic solutions. And we've also observed cleanliness requirements needing some more, I guess, investment and discussion in the industry, as a lot of the cleanliness requirements that are needed for optics were not necessary for electronics. And then finally, system implementations using CPO are very new. And the industry has become comfortable using GR468 to specify optical transceiver reliability. The industry obviously has agreement on system level strife and rel, but embedding optics in a chassis does require new stress protocols at the system level. We're happy within Broadcom to share our learnings as we also become more mature, and APC would be a great place to do this. But this is, again, another area that I think if we look further downstream, will require some more industry discussion and collaboration. I think our work, I'd like to believe our work thus far has shown that there are no more remaining technical showstoppers to deploying true co-packaging. And I think that is a meaningful step. Furthermore, the appliance ecosystem, or some of the appliance ecosystem, has embraced CPO, and they are getting a leg up on development and deployment. But most importantly, Bring Up is becoming more familiar to a wider range of developers. Next key steps are reliability, real yield, repeatability, But and of course, with that, there's going to be even more ecosystem opportunity for companies to come in and develop critical new solutions that are required. But I think looking forward to where forums like APC can take the next phases of industry collaboration. So thank you.
Thank you very much, Manish. Thank you for a great presentation, but also thank you from the very beginning believing on co-packaged optics. I think everybody knows this about me. I'm a really huge fan of CPO. I believe there were many, and there are still many challenges that we need to solve, but this, in my mind, the most beautiful way of solving it, the lack of the increased density of photonics at the data center level. So thank you very much, Manish. Let's start the Q&A. So let me ask all our other speakers to switch on the camera and look their best for the next 15 minutes. The first question is from John Smith from Photon Delta and goes to Jeffrey Maki. Is APC restricted to silicon photonics, or are other materials, like for example, indium phosphide, part of your ecosystem?
We are not restricted. We presented a mission that we're working on to make something happen in the industry. If there's interest for indium phosphide monolithic integration project of some kind, certainly we're open to it. Perhaps within our efforts, we'll find that some standards could be equally phrased for silicon photonics and indium phosphide. And certainly, as we hear in our presentation today, we're still using indium phosphide. We need lasers.
The next question goes to GlobalFoundries. The GF Photonics PDK, does it include heaters? Are they under development? When are we going to have heaters in your silicon photonic platform?
They're already available in the PDK, and I think there was a question also about the reliability. They've been pre-characterized, as I'd mentioned before. We're trying to do this work ahead of people using these components. So they're already in the PDK, including the undercut.
How fast can you tune with heaters? Is it kilohertz? Megahertz?
You would have to refer to it in the PDK.
Of course. And the next question goes to the OSAT in the room. We go to Dhiraj and Cassandra of Silitronics. Can you talk a little bit more about the wafer level test where the optical signal, the laser is piped in externally?
So on that question, what I would say is the main challenges of that are similar to that of assembly, in that there are just so many different designs. Everything's very unique. So having all of the tooling is less possible to have all at once, just given that, grading couplers, edge couplers, and any type of electrical probing, just everything's very, very different at all times.
The next question, I go back to GlobalFoundries, I go back to Vikas, is a twofold question. Can we use your PDK with different software vendors, not only the small one, but the big ones? And of course, can we also use your PDK to, are there any schedule for MPW runs today, and what is it?
Yeah, so I think the MPW runs, I think there is, the schedules are on the GF external website. And if you can't find it, just send me an email. I can put you in touch with our salespeople who can give you the MPW schedule.
All right, let's go to the next question, and the next question goes to Jabil. Let's see how we address this one, because I think it's a very good one. Noam, you mentioned the chicken and egg situation between CapEx needed to support HVM and the need for customer demand. Do you see interest from customers to co-invest? And if so, in which applications? And if not, is it because current tech is considered just good enough?
I will give a very limited answer on this. When clients have a very bespoke solution that requires custom tooling that needs to be developed just for their product, then yeah, there's either they'll consign it or there'll be some agreement. I think in order to get to the cost targets that we want, we will need some standardization, and then it cannot be super bespoke. It needs to be with some commonality to others. The other part of it that I will kind of address is that at the end, that fiber attach at the latter parts of assembly, the minimum capacity per tool is a smaller side. So you can have an easier ramp up that you buy a certain size of fleet of tools and then you gradually increase it. As you creep up closer to when you look at these advanced packaging schemes that have to do, you have to be able to handle wafers, tooling becomes much more expensive, and the throughput of every one tool is kind of geared towards the CMOS world and capacities there. So it's harder to break it up and do a gradual investment. Yeah, I don't think I could comment exactly on specific clients, and yeah,
But
they're willing to
Dhiraj really wants to comment on this, I believe.
go.
Yes, yes. So, in my past life, I used to work for AC, which is #1 in assembly and test. We have ramped up many devices at wafer level as well as packaging. So let me address between the traditional electronics IC and optical packaging. So in traditional IC, the bump size, as Vikas may say, is pretty much perfect, pretty much fixed. Normally it's 130 micron pitch, sometimes it's 150. For copper pillar, it's normally 80 micron pitch. For the ball size, it's like 0.2, 0.3, 0.4. It's pretty fixed. Wire diameter is pretty fixed. So all these in electronics IC packaging is already fixed. So whether NVIDIA or Broadcom or Qualcomm, Apple, anybody designing electronics IC, the package size is perfect. It's fixed. They know what is the design rule and they can ramp up. On the Photonics IC, we have worked with multiple customers. None of even customers among themselves, when they're going from 100G transfer module to 200G transfer module, the die size is different, the number of FAU is different, the size of the PIC is different. So there are so many variables. Forget about the technology, the variable in the package itself. So it's very difficult for OSAT or the CMs to invest because the customer itself is keep changing the device size, the form factor, the thickness, the FAU. So I think it's very difficult to invest big time to ramp up the capacity. Till customer says, you know what, I'm going to have a fully consigned capacity for myself, and they are responsible for it. So that's one of the reasons people like AC or MCore not able to step up, because I think it is another, in my opinion, 3 to 5 years before the industries, have the optical package size stable, and then people like Ficontec or whoever can step up and then bring in the equipment, and we can have the true volume in millions or billions of units, per year. So,
This question,
but it's
I
a
want
good
to go.
area to be.
I want to go
But
back
it's a
to
good area
Broadcom
to
now.
be.
We have a lot of questions in the room about chiplets. Everybody's talking about chiplets these days, and they consider that the role of photonics will be the interconnection between chiplets. From the Broadcom side, do you see the need to go towards a certain level of standardization to drive the optical chiplet interconnect?
So we've started by looking, #1, at applications that are inherently optical to begin with. So a lot of what's emerging, let's say for sort of the next generation chiplet interconnect for optics, are looking at some of the applications that we have not been targeting. So in this case, the interconnect, say, between your ASIC, like take CPO, for example, which is inherently a chiplet architecture, but you're using a traditional connection of, say, an LR SerDes or something of that nature for the connection. I think for networking applications, that is still the methodology that we see kind of persisting over the next few generations. I would not be the right one to comment on what we may see after that for some of the more advanced compute applications once you start trying to do chip-to-chip optical, connectivity on a die level or at a package level. So
there are many more questions in the chat. Allow me not to continue with them. Many questions about acquisitions, many questions that I'm not going to address on this, but I'm going to encourage all the people here to answer the questions themselves in the chat so everybody can get their answer. But now, there is time to give the floor to a very dear friend of mine, a person who has meant a lot in my career, Melissa Carlos. Thank you very much for this opportunity of sharing this webcast of the Advanced Photonic Coalition. I would like to give you the floor to tell us what's next with APC.
I can tell you it's collaboration. Without us all collaborating as an industry to move forward the challenges that we have, to overcome any design or manufacturing situation, it's all of us working together towards a common goal. And that's really it. It's collaboration to overcome our current challenges and meet the needs of this industry. Thank
And
you.
of course, all of us are going to San Diego for OFC. Jeffrey Maki, what's going to happen with APC during OFC?
We will have a panel in the trade show floor, and the panelists will be further exploring what's happening in this area. So we haven't completely finalized the content of the panel, but we'll be there.
And I will be there as well. Of course, OFC is the place to be, but it's still 2 months ahead. If you have any questions for APC, contact Melissa Carlos and Jeffrey Maki. You have any questions about Optica, contact me. But most important, if you have any questions about the supply chain of photonics for AI, contact Manish Mehta from Broadcom, Propstra from Quantifi, Vikas Gupta from GlobalFoundries, Dhiraj and Cassandra from Silitronics, and Torsten Varenkamp from Ficontec. It has been an honor and a pleasure being with you today, morning, afternoon, and evening in the world. It was a global event. Thank you. Until the next time, take care of each other. If you have to wear a mask, recover from your cold, and see you at OFC. Bye-bye.
Thank you for watching.